Welcome back, everyone, to Fly Vehicle Dynamics. This is lecture 36 in the last week, week number 15. So I want to talk a little bit more about the longitudinal dynamic stability, studying the example that we were seeing in lecture 35. So we saw that we highlighted two flight modes. One called the short period mode, which affects mainly the angle of attack, the pitching rate, and the pitch angle. And while this mode affects these three states, it doesn't really affect the surge speed. Therefore, if only this mode was acting, the component u of the velocity would remain constant. This mode, we saw that is characterized by a short period, or which is the same thing as saying high frequency, and it is also highly damped. Therefore, the effect of this mode died down pretty quickly. On the other hand, the other mode, the other flight mode that we saw is the phugoid mode, which affects mainly the surge speed and the pitch angle, and the alpha and q are almost constant when this mode is activated, let's say. And the phugoid mode is characterized by a low frequency, so the period is very large, and we have a low damping. So the phugoid mode, if activated, is protracted for a long time. So if we would just leave the aircraft to fly at its own accord, it would continue to oscillate in the XZ plane, going, remember that the motion is sort of an up and down a roller coaster, and it would be quite uncomfortable for the passengers. Therefore, usually there are some active controls in order to kill this oscillations. Yes, and as I said here, both of these modes involve a pitching movement of the aircraft. Whereas, while the phugoid mode is quite obvious because you would go up and down for several hundreds of meters, the short period mode dies down in just a few seconds. So probably you wouldn't even feel that. Okay, so continuing with the example that we saw, pretty much now we want to solve the linear system. So we have two ways. We have the direct way. We could just numerically integrate the equation using MATLAB, for example, and finding the solutions. So x of t. And of course, we need some initial conditions in terms of state and in terms of control. And remember that here state and control, x and dx would actually be, x and u should actually be delta x and delta u, because those are the perturbation from the trim condition. Well, we also saw that instead of solving the system numerically, we can actually solve it analytically and gather some information. The fact that we found the flight modes is because we transform the original linear system into another linear system, solving for the modal amplitudes, etas. So we can, as we saw, solve the system analytically, and once we have the solution to the system would be eta of t, we can use the modal transformation to retrieve the states. X of t equals m eta of t. And M, of course, is the modal matrix that comprises the eigenvectors of the matrix A. Now, continuing with the example, we're going to choose particular values for the initial state and for the initial control perturbations. So to make things easier, we're going to choose an initial state perturbation equal to 0. So we are not perturbing the aircraft in terms of surge speed, angle of attack, pitch angle, and pitching rate, but we're applying only a change in the first term of the control vector. And if you recall that is the elevator deflection. So in other words, we are going to deflect the elevators upwards by 1 degree. And why is it degrees and not radians? Well, because if you go back to lecture 35, we defined the states in terms of degrees. So this is also going to be in degrees. Of course, if it was in radians, that you would have to apply a transformation to make everything in radians. And in the handout, there is something like that. Actually, in the handout, you'll see that the original A and B matrices are provided in radians, and a transformation is applied to go from radians to degrees. And it's not a straightforward transformation in terms of multiplying each element of the matrix by 180 divided by pi. You know, usually if you want to go from radians to degrees, what you do, you multiply by 180 divided by pi. You don't do this element-wise. So if you want to take a look, it's in the handouts. I don't really care for you to know it, so I'm not going to ask it in the exam. All right. So let's set up everything to solve the system analytically. And of course, now I mean the model system, because that's the one that we can solve analytically. So we need to find the initial conditions for this ODE system. And of course, the initial condition, eta 0, is going to be given by the initial conditions in terms of state, x0, pre-multiplied by the inverse of the modal matrix M. Here, even if we didn't know the modal matrix, since all the states, the initial condition for the states is a 0 vector, then of course eta 0 is also going to be a 0 vector. But nevertheless, we're going to still use the modal matrix. And I'm not going to write it down in terms of components because it's just a little bit lengthy, but the expressions for the eigenvectors v1, v2, v3, and v4 are given in lecture 35, so you can find the values for the eigenvectors over there. Here, instead, I reported the inverse of such matrix. And so, of course, I'm not going to read it term by term, but this is just the inverse of such matrix. Then if you follow here the development of this new system, you see that we have to compute M inverse times B. That's why I provided M inverse in the first place. So M inverse times B, and in the handouts, it is written as a B tilde. And this is going to be, so M inverse is a 4x4 matrix, B is a 4x2 matrix, therefore B tilde is going to be a 4x2 matrix also. And here you have the entries. And we can also give them the name B tilde 1, 1, B tilde 1, 2, and so on and so forth. Now, before proceeding, I want to point out one thing. Normally, there will be a bunch of ordinary differential equations that describe the control dynamics because in the original system, we have the dynamics of the state that depend on the state itself and on the control. But how does the control vector vary? Well, the control vector varies according to its own law, if you wish. So its own dynamics. And that is usually described by another linear system, which is dependent on the state and on the control itself. So you'll find if you study later on just the controls, then you're going to be given the first system with the x dot and also the control system, because that's what you want to design in order to keep the aircraft or any machine at a certain state. Here we are just analyzing the behavior of the aircraft left on its own, so without any control. So the only control deflection or input that we're giving is just a perturbation. So we're not, and that remains fixed. And let me explain it a little bit further here. This U0 is the initial perturbation in the control, and we're gonna assume that that remains static, so that -1, so the deflection upwards of the elevator remains constant. And so we want to see how the aircraft behaves if the elevator remains stuck at -1 degree. So we want to see how the state develops. So we're not really concerned about the control response. And so technically, you would have this new set of equations, but here we consider that the C matrix and the D matrix, which are matrices of 2 by 4 and 2 by 2, are 0. Therefore, U dot is 0, and that means that the control U is constant, and that is equal to its initial value. And that's exactly what I said in words. The control is going to remain fixed at its initial value. And that will simplify the calculation of this integral, because now U of tau is constant and can be taken out of the integral along with M inverse NV. So the only thing that we really have to compute, especially for this example, since eta naught is 0, so this first term just all goes to 0, all we're left with is to integrate from 0 to t the transition matrix e to the power of capital lambda to the power of, multiplied by t minus tau in d tau. So since, as I said, let me use another color. This term M inverse times B times U is constant. We can pull it out of the integral, and that is equal to B tilde U naught. And so we only have left integrating the matrix, which is pretty straightforward. We can do it element-wise. And let's take in general the integral of e to the power of lambda times t minus tau. And remember that lambda is the eigenvalue of A, whichever here. It doesn't really matter. I'm just solving for one of the for diagonal elements. Well, you can follow the integration. I don't really have anything to add here, just to tell you that the result is 1 over lambda times e to the power of lambda t minus 1. If this is not clear, please, ask me. But otherwise, I'll assume that you guys are familiar and with solving integrals. All right, so we pretty much have everything, because again, the first term goes to 0, and then the second term involving the integral has a bunch of stuff that are constant, and then the integral of the matrix is just the integral of these 4 elements, diagonal elements, which turn out to be 1 over lambda times e to the power of lambda t minus 1. So now we have the vector b tilde u naught, and here I'm giving it the numerical values. Therefore, we can write down the solutions for the modal amplitudes, eta 1 all the way to eta 4. And right here, I gave a little analytical expression, like a formula, and to the right, we have the actual numerical expression. But still, we did it analytically. I might have computed, used the calculator to multiply numbers or find the, the eigenvalues or eigenvectors. But what I wanted you to notice that we haven't numerically integrated the system, we've solved it analytically. All right, so once you have the 4 modal amplitudes, we can retrieve the states by multiplying the modal amplitudes by various elements of the eigenvectors, as I've already showed you in a couple lectures ago. And in this case, we have the surge speed, u of t, is equal to eta 1 of t times v11 plus eta 2 of t times v21, so on and so forth. And what are these v11, v21, v31? Well, let's take, for example, v21 is the second element, the first element of the second eigenvector, v2. Or let's take another one, v34. So you take the eigenvector number 3 and take the 4 element of it. So we have everything. We have the eigenvectors, we have the modal amplitude, so we can reconstruct the actual states. So the first one, as I said, is the surge speed. Then we have the angle of attack, the pitch angle, and the Q rate. Now, in this figure, I plotted the solutions, so the states, found analytically, and I've used the blue color for that, for the analytical solution. And then I've also solved the original system, the x dot equals ax plus bu, numerically using MATLAB. And I've plotted that solution with the orange dashed line, and you see that there's the two solutions are the same, okay? So if you just wanted the time history of the states, you can go directly and solve the original system numerically, or you can do it analytically. So what is the benefit of solving the system analytically through the modal transformation? Well, it gives us more insight into what's going on in terms of modes and why the states develop in a certain way. So remember, here we have only two modes. We have the short period mode that dies down pretty quickly, and it's a high frequency mode. And then we have the fugoid mode that extends for much more time, and it's just slightly damped. And we can see that if we look at the plots themselves. In fact, when we look at the time history for the angle of attack, then the pitch angle and the Q rate, we have in the beginning the effect of the short period mode. It cannot really see it for the pitch angle, but we're going to see it better later when I show you the plots on MATLAB. But it's more evident for Q. You see the little spike here at high frequency. That is the effect of the short period mode. And then after that, the fugoid mode is kicks in, and the shape of the curves, you know, resemble the fugoid mode characteristic in terms of period. For example, if we take theta, this period from peak to peak is about 30 seconds, and the period, in fact, of the fugoid mode was 29.3 seconds. So that's exactly the characteristic of such mode. All right, so I forgot that I actually zoomed in the first part so we can actually see things a little bit better. Well, U, the component U, the velocity, is not affected by the short period mode, and in fact, you see here the curve is pretty smooth and doesn't have any particular behavior in the beginning. Whereas for an angle of attack, you see this little sudden increase in the beginning. That is characteristic of the short period mode. And you can slightly see it on the pitch angle, and it's definitely more pronounced for the Q component of the angular velocity. All right, so now let's just focus on one of the states, namely the angle of attack, and let's divide the contribution of the short period mode and the fugoid mode. So remember, the short period mode is the contribution of amplitude, modal amplitude 1 and 2. So I'm going to just take the absolute value of that. So eta 1 times V12 plus eta 2 times V22 in absolute value is the contribution towards the angle of attack due to the short period mode. And the remaining part, namely eta 3 times V32 plus eta 4 times V42, is the contribution due to the fugoid mode. And if we plot that, you can see that it's pretty much we've separated, we've taken this curve here for the angle of attack, and we've separated the contribution of the two modes. And we can do that because if you remember the two modes in the complex plane, we had the fugoid mode with two eigenvalues over here, while the short period mode had the two eigenvalues over here. They're pretty separated, so the contribution of each mode is quite distinct. And we can see that when we in fact separate the short period mode contribution to the angle of attack, which is this red curve, in contrast with the contribution of the phugoid mode. So short period mode, it's sudden, it's quite steep in the beginning, high frequency, but dies down pretty quickly and then remains constant. All right. Whereas the phugoid mode, it's oscillating and with a much longer period, as we expect. And we can also plot the percent contribution of the short period mode and the phugoid mode. And you see then in the beginning, when the short period mode is acting way more than the phugoid mode, we'll have that the majority of the angle of attack, the change in the angle of attack is due to the short period. And then as time increases, then the short period contributions dies down and then it settles to about 70%, whereas the phugoid mode contribution settles down to about 30%. All right, so this concludes the analysis of the dynamic stability. At least, we saw this example. So just to recap, for the dynamic stability in terms of the longitudinal motion, we have two flight modes. One is the short period mode, and one is the phugoid mode. Now, what I want to do is I want to go to MATLAB, and I want to show you guys how you can obtain these plots and do all these calculations using a simple code. I haven't really commented that, so I want to do it right now, and I've attached it to the week 15 page, so you can find the codes over there. So once again, I haven't commented it, so you kind of have to either watch this explanation that I'm going to give or figure it out yourself. So let's go to MATLAB now. Okay, so we have our code over here. So I wrote down the A matrix and the B matrix. That's pretty straightforward. Then calling the function EIG of A, here the output of this function are two matrices, M and D, and M contains the eigenvectors of A, and D is a diagonal matrix containing the eigenvalues of A. So M is the same symbol that we've been using for the model matrix, and D is actually the capital lambda matrix. So let's just run the code till here, and let's see the output. So you see we have the model matrix with the first eigenvector is the first column of M, the second eigenvector is the second column of M, and so on and so forth. And you'll see that D is a diagonal matrix. The only non-zero elements of D are the diagonal elements containing the first, second, third, and fourth eigenvalues. So you see that we have two pairs of complex conjugate eigenvalues as expected. So now let's move on with the code. The next 4 lines, I'm just assigning the first column of M as V1 as the first eigenvector, and then second column is V2 and V3 and V4. And then L1 is the eigenvalue 1, and so well, we can write it down like this. So eigenvectors And these are the eigenvalues. All right, so now I've computed the natural frequency associated with the first pair of complex conjugate eigenvalues. So for the short period mode eigenvalues, along with the period and the damping ratio. And same thing for the second pair of complex conjugate eigenvalues. And in the first figure, I'm plotting the actual eigenvalues. So let's see what we get. I'm plotting them on the complex plane. And these are all the plots that I've already attached to the lecture notes, but I'm showing you how I've got them. All right, so we have the green eigenvalues are the phugoid mode eigenvalues, and the red ones are the short period mode eigenvalues. I haven't added a legend. You can go ahead and do that. But in the notes, everything should be clearer. All right, so now what I'm doing here, I'm computing the phase, you know, this theta 1, 1, theta 1, 2, and the so I have the phase and the magnitude for all the components of the eigenvectors elements. So for V1, if you have V1, it has 4 components, and all 4 of them are complex numbers. So we saw that, and they're written in a Cartesian form, so we can transform them into polar coordinates. And the polar coordinates would be magnitude times e to the power of j times the phase. So we have to find the phase and the magnitude of such complex numbers. So I've done that for all the elements of V1, then for V2, V3, and V4, and same thing for the magnitudes. Actually, I haven't done it for V2 and V4 now that I've noticed, but it's not really a big deal because V2 and V4 are complex conjugates of V1 and V3. So once you complex conjugate complex conjugate numbers have the same magnitude. 1 plus 2j has the same magnitude of 1 minus 2j. So it doesn't really matter. And in fact, in the next 2 figures, figure 2 and 3, I'm computing the phasors. And if you remember, I've done it only for eigenvector number 1 and number 3, because eigenvector number 1 and eigenvector number 2, they give the same phasors. It's just with the symmetry about the x-axis. And same thing for eigenvector 4, it gives the same information that we get from eigenvector 3. And that's because, once again, they come from pairs of complex conjugate eigenvalues. And let's see what we get. You should already know that because I've attached these plots in the notes, but this is how you find the phasor plots. So figure 2, that is for the short period mode, and then figure 3 for the phugoid mode. Okay, so now we are ready to solve the actual linear system. And so, as anticipated, we can do it in 2 ways. We can do it analytically and we can do it numerically. So I've done it in both ways here, starting with the initial conditions in terms of the state perturbation, all equal to 0, and then the control perturbation equal to -1, 0. Then eta 0 is m backslash x0, and m backslash is equivalent of m inverse. It's just computationally better to write it this way rather than inv of m. Now we have this b till u is actually m inverse times b, which would be b tilde, times u0, and well, it's pretty clear from how it's written. And so the analytical solutions for N1, N2, N3, and N4, and I'm doing it, I've created a vector of discretized a time vector from 0 to here 200 seconds in intervals of 0.01 seconds. So I'm creating vectors containing the modal amplitudes eta 1 to eta 4 here. Of course, I wrote them down as N1 through N4. And here I've included also the first part, just in case that your initial state is non-zero. So this is a more general form. So you can just change the initial condition in terms of state and vector, and it will work. So once you have the modal amplitudes, you can create the states, u, alpha, theta, and q. And over here, there are the contributions of u, alpha, theta, and q due to the short period mode or the phugoid mode. So that concludes, this part concludes the analytical solution of the system. Now, if we want to solve the original system numerically, we just call the AE35 function as usual. And so we need to find, write the ODEs in a separate function. We don't need to use a separate file because this function is very short. So I've just written it at the end of the script, and let's go directly there. So once again, here we have the input is the time and the state, and I'm passing also parameters, the A and B matrices, and the control U0, the initial and final time of integration, and the initial condition in terms of state. So here it is. This is all you really need. U is constant and is equal to U0, so x dot is equal to AX plus BU. You see that, if you really want it, if you're just interested in the solution of the original linear system, then you can just solve it numerically, and that's it. It's much easier. It's only 5 lines of code. Of course, it's a little bit more when you want to plot things. Figure 4 is going to plot the states solved analytically and named with U, alpha, theta, and Q, and numerically with X1, X2, X3, and X4. And then well, let's just see that first. And we go in figure 4, we have the plots that you saw in the notes earlier, with the 4 states solved numerically and analytically. You see the solution is exactly the same. So both ways are fine. Don't worry about these warnings here. That is because when MATLAB is multiplying, adding complex numbers, there are going to be some numerical errors. So although in the end the states should be purely real, they will likely have some imaginary tail. It's very, very small. For example, let's see alpha. It has some imaginary part, but it's so small that here it's 0, 0, 0, 0. We should really see with the long format, but it's so small that it's pretty much 0. But for MATLAB, it's telling you, watch out, this these values are complex, so I cannot really plot complex numbers. I'm just gonna plot the real part. It's fine because the imaginary part is really, really small. But always check it and double check what you're doing. Then here from figure 5 through 8, I've plotted the states in terms of the contribution due to the short period mode and the phugoid mode. What I showed you earlier was just the angle of attack, but I did it for all 4 states. So we can see that. Here's figure 8 is for Q. So you see once again that it's pronounced. The contribution of the short period mode is just in the very beginning, and then it gets to a constant, whereas the contribution of the phugoid, you see it oscillates because that's what the phugoid mode does. Then we can analyze this is the pitch angle, and in the beginning there's a little bit of a short spike due to the short period mode, but overall it's the phugoid mode that commands the contribution towards the change in pitch angle. And then we have alpha that we've seen, and U. So this is very interesting because U is not affected almost at all by the short period mode, and that is pretty evident because you see it pretty much the contribution of U due to the short period mode is pretty much 0 throughout the all the time from 0 to 100 and even further. And in fact, if you see the second subplot, the contribution goes quickly to 0 and stays there, whereas the contribution due to the phugoid mode is pretty much 100% all the time. All right, so this is all for today. Next time, we're gonna see the same example, the same airplane, but we're gonna study the directional and lateral dynamic stability. And I'm going to provide the same plot. So the analysis is pretty much the same, but we're obviously gonna find new flight modes. And I'm going to anticipate that instead of having 2 modes, we're going to have 3 modes. And so the only way for 3 flight modes to arise is that if 2 of them are real, so 2 real eigenvalues, and a pair of complex conjugate eigenvalues. But we're going to see more on Wednesday. And then if I finish everything by Wednesday, which I think I'll be able to do that, we can also use Friday for Q&A in preparation for the final. All right, this is all for today, and I'll see you virtually very soon. Take care.